Welcome to this walkthrough. In this video, we'll be tackling LeetCode problem number 1805, number of different integers in a string. This problem challenges us to extract and count unique integers from a string, which is a great exercise in string manipulation and efficient use of data structures. Let's dive in. In this problem, you are given a string called word, which contains a mix of lowercase English letters and digits. Your task is to extract all the integers from this string and determine how many unique integers are present when considering their numerical values. It's important to remember that leading zeros in integers should be ignored, so for example, the strings 0, 0, 1 and 1 both represent the same number. The input to the problem is a non-empty string composed of letters and digits, and the output is simply the number of distinct integers found in the string. For instance, if the input string is word equals A123 BC34 D8F34, the extracted integers are 123, 34, 8, and another 34. Since we are only interested in unique numerical values, we remove duplicates, leaving us with 123, 34, and 8. This gives us a total of 3 distinct integers, so the output would be 3. Another example is the input word equals LeetCode 1234 code 234. Here, the extracted integers are 1234 and 234. Both are unique, so the total distinct integers are 2, and the output is therefore 2. Now, let's consider a more nuanced case with the input word equals A1B01C001. The integers extracted from this string are 1, 0, 1, and 0, 0, 1. While these appear different in their representations, they all have the same numerical value of 1 when leading zeros are ignored. As a result, only one unique integer exists in this case, and the output is 1. To summarize the explanation for this last example, the integers 1, 0, 1, and 0, 0, 1 are all treated as the same number because leading zeros do not change the numerical value. This means after removing duplicates, the only unique integer left is 1, giving a total count of 1. The problem also comes with several constraints and edge cases. For example, if the string contains no digits at all, the output should be 0. Similarly, if all integers in the string are numerically the same but represented differently, only one unique value is counted. Efficient handling of longer strings, up to the limit of 1,000 characters, is also essential to solve this problem effectively. To begin solving this problem, we first considered the brute force approach. The intuition here is straightforward: traverse the string character by character, extract all sequences of digits as substrings, and convert each one into an integer. By converting to integers, we naturally eliminate leading zeros. These integers are then added to a set, which automatically handles duplicate values. Finally, the size of the set gives us the count of distinct integers in the string. The steps for this approach are systematic. First, traverse the string and identify contiguous digit sequences. Then, extract these sequences, convert them into integers, and store them in a set. The final step is to return the size of the set. In terms of complexity, this approach is linear in time because we traverse the string once and perform constant time operations for adding elements to the set. However, the space complexity depends on the number of distinct integers we extract, which is proportional to the size of the set. While this method is simple and efficient for smaller inputs, it does have trade-offs. It requires additional memory to store the set, and if the set of numbers becomes very large, performance might degrade. Additionally, the implementation involves manual substring handling, which can be tedious for larger or more complex strings. Now, to simplify the implementation and overcome the limitations of manual traversal, we can use an optimized approach that leverages regular expressions. The intuition here is to use regex to extract all contiguous digit sequences in a single step, which eliminates the need for manual substring management. The steps are straightforward. First, use a regex pattern like \d+ to match all sequences of digits in the string. Once we have these matches, convert each sequence into an integer to remove any leading zeros, and add the integers to a set to handle duplicates. Finally, return the size of the set. The time complexity of this approach remains linear because regex matching operates in O(n) for this problem, where n is the length of the string. Similarly, the space complexity depends on the number of distinct integers extracted, as they are stored in the set. The trade-offs include the need for familiarity with regex, which might be challenging for some developers, and a slightly higher constant overhead due to regex processing. However, this approach is much cleaner and avoids the repetitive substring handling seen in the brute force method. There's also an alternative approach worth discussing that uses a two-pointer sliding window, which we'll explore next. The two-pointer sliding window approach provides another way to solve the problem without relying on regex or additional libraries. With this method, two pointers are used to identify digit substrings directly within the string. When a non-digit character is encountered, the substring between the two pointers is processed as a potential integer. These digit substrings are then converted into integers and stored in a set. The process continues until the entire string is traversed, and finally, the size of the set is returned. This approach still has linear time complexity since the string is traversed once, and the space complexity remains proportional to the number of distinct integers extracted. The trade-offs here are that while this method avoids the need for regex, it requires careful implementation. Managing the pointers and handling edge cases, such as adjacent non-digit characters or strings that start or end with digits, can make the code more error-prone and verbose. Given these considerations, we ultimately selected the regex approach as the optimal solution. It offers a balance between efficiency, clarity, and simplicity. Let's take a closer look at why regex was chosen and some key insights that shaped our strategy. When comparing the approaches, each has its strengths and weaknesses. The brute force method is simple but involves repetitive substring handling, which can become cumbersome. The regex-based solution is clean and concise, leveraging a powerful tool to simplify digit extraction, but it does require familiarity with regex syntax. The two-pointer approach, while efficient in memory usage, is more complex to implement and prone to errors due to the careful pointer management it demands. Ultimately, regex strikes the best balance among these factors, providing a solution that is both efficient and easy to understand. A key insight in this problem was recognizing that integers are naturally deduplicated when stored in a set, and converting digit substrings to integers removes leading zeros effortlessly. This realization, coupled with the use of regex for concise processing, was the aha moment that made this approach stand out. By taking advantage of these observations, we've chosen a strategy that is not only optimal but also intuitive to implement for a wide range of problem scenarios. The problem we're tackling is to count the number of distinct integers present in a given string. This string can contain both letters and numbers in any order. An integer is defined as a sequence of digits appearing contiguously within the string. One crucial detail to note is that leading zeros in these numbers are ignored when determining uniqueness. For instance, 00123 and 123 are considered the same number. To solve this, we'll break the problem into clear steps. First, we need to initialize our data structures. We'll use a set to store the distinct integers because sets automatically handle duplicates for us, meaning we don't need to write extra logic to check for repeated numbers. Additionally, we'll use an empty string called current_number to build each integer as we process the string character by character. This setup lays the groundwork for the rest of the algorithm. Now, we start traversing the input string, one character at a time. For each character, there are two possibilities. If the character is a digit, we append it to current_number, which allows us to build the integer incrementally. On the other hand, if the character is not a digit, it means we've reached the end of the current integer. In this case, we first check if current_number is non-empty. If it is, we convert it to an integer, which automatically removes any leading zeros, and then add this integer to our set. After that, we reset current_number to an empty string so that we can start building the next number. When the loop finishes, there's one last detail to handle. If current_number still contains digits, we convert and add it to the set as the final integer. Once all characters have been processed, the size of the set gives us the count of distinct integers, which we return as the result. This algorithm has a few key aspects that make it both efficient and robust. First, when we convert current_number to an integer, Python automatically removes leading zeros, which simplifies our implementation and ensures numbers like 00123 and 123 are treated as the same. Second, using a set is highly efficient because it handles duplicate integers automatically and operates with an average time complexity of 0.1 for insertions. This ensures our algorithm remains fast even with large inputs. Additionally, the algorithm gracefully handles edge cases, such as strings with no digits, strings made entirely of digits, or strings with mixed alphanumeric characters and multiple delimiters. The two main data structures we rely on are the set, which stores unique integers, and a string variable for dynamically building numbers during traversal. In terms of complexity, the algorithm runs in O(n) time, where n is the length of the input string, since each character is processed exactly once. The space complexity is O(k), where k is the number of distinct integers, as that determines the size of our set. Let's walk through an example to see this algorithm in action. Consider the input string A123BC34D80F34. We start with an empty set and an empty current underscore number. As we traverse the string, we skip non-digit characters like a. When we encounter 1, we start building current underscore number as 1, then 12, and finally 123 as we process consecutive digits. When we hit the non-digit B, we know we've finished building the number 123, so we add it to the set and reset current underscore number. This process continues for the rest of the string. For instance, we build 34 foot after encountering the digits 3 and 4, and add it to the set when we hit a non-digit. Similarly, 8 is added to the set when we encounter the non-digit E. At the end of the string, we ensure any remaining number, like the final 34 foot, is added to the set. The final set contains the numbers 123, 34, and 8. Finally, the size of the set, which is 3, represents the count of distinct integers in the string. This is our output. To optimize the algorithm further, we ensure that the conversion of current underscore number to an integer is only performed once, right before adding it to the set, reducing redundant operations. Additionally, we can minimize branching overhead by using concise checks for non-digit characters during traversal. These optimizations make the algorithm both clean and efficient, ensuring it performs well even for large and complex inputs. This implementation solves the problem of finding the number of distinct integers in a string using Python. Let's break it down step by step. 1. Importing the re module. We use Python's re module for regular expression operations. Regular expressions are crucial for extracting sequences of digits from the input string efficiently. 2. Defining the function number different integers. This function takes one argument, word, which is the input string containing alphanumeric characters. 3. Using reFindAll to extract digit sequences. The regular expression \d plus matches one or more consecutive digits in the string. The reFindAll function returns a list of all such matches. For example, if the input is A123BC34D80F34, the result of this step would be 123, 34, 8, 34. 4. Converting sequences to integers and removing duplicates. Using a set comprehension, we iterate over the list of digit sequences. Each sequence is converted to an integer using int number. This automatically removes any leading zeros, as Python's int function does not preserve them. Additionally, since we are using a set, duplicate integers are automatically removed. For instance, 123, 34, 8, 34 would result in the set 123, 34, 8. 5. Returning the count of unique integers. Finally, we return the size of the set unique underscore integers using len, unique underscore integers. This gives the total number of distinct integers in the input string. This approach is efficient and concise. The regular expression efficiently identifies digit sequences, and the use of a set ensures that duplicates are handled naturally. The time complexity is approximately O(n), where n is the length of the input string, as we process each character once during the extraction and set operations. The space complexity is O(k), where k is the number of unique integers in the string. Here, we begin our Java implementation by importing the necessary utilities and defining our solution class. The main method, number different integers, accepts a string called word as its input. To identify and store unique integers from this string, we use a hash set, which ensures that only distinct values are retained. Additionally, we initialize a string builder named currentNumber to help extract sequences of digits as we iterate through the string. The for loop processes each character in the input string. If the character is a digit, it gets appended to currentNumber. However, if the character is not a digit, this indicates the end of a number sequence. At this point, we check if current number contains any digits. If it does, we process the number by adding its stripped version, removing any leading zeros, to the hash set. After that, the string builder is reset to prepare for the next potential number. This ensures that we handle sequences of digits and non-digit characters correctly as we traverse the string. Finally, after exiting the loop, we perform one last check to ensure no number is left unprocessed. If current number still contains digits, we add it to the hash set after removing any leading zeros. The unique integers hash set now contains all distinct integers extracted from the string. The method concludes by returning the size of the hash set, which represents the total count of unique integers. To handle leading zeros in numbers, we define a helper method called strip leading zeros. This method converts the string representation of a number into an integer, which automatically removes the leading zeros, and then converts it back to a string. This ensures that numbers like 0, 0, 1 and 1 are treated as the same value. The implementation is now complete and efficiently extracts and counts unique integers from the given input. Let's walk through the first example where the input string is word equals A123BC34D80F34. The first step is to extract all sequences of digits from the string. Using the regular expression \d+, we can identify these sequences. Here, the digit sequences extracted are 123, 34, 8, and another 34. Next, we need to remove any leading zeros and ensure we only keep unique integers. By converting each string into an integer using the int function, leading zeros are automatically stripped, and we get the values 123, 34, 8, 34. To eliminate duplicates, we store these integers in a set, resulting in 8, 34, 123. Finally, to determine how many unique integers are present, we calculate the size of the set. This gives us the count of unique integers, which is 3. The first example concludes with a unique integer count of 3, which is also the output of the function for this input. Now, let's move on to a second example with the input string word equals LeetCode code 234. The process is the same. Using \d+, we extract all digit sequences, which gives us 1234 and 234. These strings are then converted to integers, and we obtain the list 1234, 234. Storing these in a set removes any duplicates, resulting in 1234, 234. The length of this set is 2, so the unique integer count for this input is 2. As you can see, the approach is consistent and handles different input structures effectively. In the third example, the input string is word equals A1B01C001. The same steps apply here. First, using \d+, we extract the digit sequences 1, 0, 1, and 0, 0, 1. These are then converted into integers, and after stripping the leading zeros, all three strings result in the value 1. This gives us the list 1, 1, 1. When we store these integers in a set, duplicates are removed, leaving us with just 1. The size of this set is 1, so the unique integer count for this input is 1. This example highlights how the solution handles cases where the same number may appear in different forms with leading zeros. To summarize the solution, it works by leveraging regular expressions to extract all digit sequences from the input string. These sequences are converted to integers, which removes any leading zeros automatically. By storing these integers in a set, duplicates are filtered out, leaving only unique integers. Finally, the size of the set is calculated to determine the count of unique integers. This approach ensures that we handle a variety of input scenarios efficiently and produce the correct result for all cases. To analyze the time complexity of this solution, we can break it down into 3 main steps. First, we use the refinal function with the regular expression \d+ to extract all digit sequences from the input string. This regular expression scans the entire string, examining each character to identify contiguous digit sequences. If the input string has a length of n, the regex engine processes each character exactly once. Therefore, the time complexity for this step is O(n). Next, we convert the extracted sequences into integers using the int function. If there are k digit sequences, and each sequence has an average length of m, the conversion takes O(m) time per sequence. This results in a total time complexity of O(k*m). In the worst case, where the entire string consists of digits, k is 1 and m equals n, making this step O, n. Even in the average case, k*m remains proportional to n, so this step is also O, n. Now, once we have the integers, we add them to a Python set. Adding an integer to a set has an average time complexity of O, 1, assuming the hash function is efficient. If there are k integers to insert, and all of them are unique, we perform k insertions, giving this step a time complexity of O, k. Since k is proportional to n, the time complexity of this operation remains O, n. When we combine the complexities of all these steps O, n, for finding digit sequences, O, n, for conversion, and O, n, for set insertion, the overall time complexity of the solution is O, n. Now let's analyze the space complexity. First, consider the storage used for digit sequences. The refindAll function returns a list of all sequences, which requires space proportional to the total number of characters in these sequences. If there are k sequences with an average length of m, the space required is O, k*m. In the worst case, where the entire string consists of digits, k is 1 and m equals n, resulting in O, n, space. Next, consider the space used by the set to store unique integers. If there are k unique integers, the space required depends on the number of digits in these integers. Assuming the average length of a unique integer is m, the space required for the set is O, k*m. In the worst case, the set contains only one large number, which requires O, n, space. So, these two components contribute to the total space complexity. Additionally, there is temporary storage used during the conversion of digit sequences into integers. The int function creates temporary integer objects, which also require O, k*m, space. However, since these objects are reused and eventually added to the set, they do not contribute to the overall space complexity. When we combine all the space requirements, we have O, n, for the digit sequences, O, n, for the set, and temporary storage that does not increase the overall complexity. Thus, the total space complexity of the solution is O, n. Let's compare this optimized solution to a brute force or naive approach. A brute force method might involve manually iterating through the string, extracting digit sequences, and checking each one for uniqueness. This would often result in nested loops or additional data structures, leading to a higher time complexity, such as O, n squared. In contrast, the current solution efficiently uses built-in functions like refindAll and int, and leverages the hash-based set for uniqueness, achieving a much more optimal time complexity of O, n. For best case, average case, and worst case scenarios, the time complexity remains O, n. For example, if the string contains no digits, the regex search completes quickly, and the set stays empty. If the string has a mix of digits and non-digits or consists entirely of digits, the solution still processes all characters linearly, ensuring O, n, time complexity across all cases. Finally, let's summarize the time and space complexity with a mathematical proof. The dominant factor in this solution is the linear scan of the string performed by refindAll, which contributes O, n. Subsequent operations, such as converting the digit sequences to integers and inserting them into a set, are proportional to the number of digit sequences. Since the number of digit sequences is bounded by the length of the string, these operations are also O, n. Therefore, the overall time complexity of the solution is O, n. Similarly, the space complexity is dominated by the storage required for the digit sequences and the set. Both of these are at most O, n, leading to an overall space complexity of O, n. This demonstrates that the solution is both time and space efficient for the problem at hand. One of the most common mistakes when solving this problem is failing to account for leading zeros. For example, if you encounter 007 in the string, it's important to recognize that numerically, this is just the number 7. Treating it as a unique value separate from 7 will lead to incorrect results, as leading zeros don't change the value of an integer. Another issue arises when overlapping substrings are ignored. For instance, in a string like 12,345, substrings such as 234 could easily be overlooked, even though they contain valid numbers. It's also critical to properly handle non-digit characters. Sometimes, people assume the string only contains digits and fail to filter out letters or symbols. Non-digit characters should act as natural delimiters, helping you identify where one number ends and another begins. Finally, avoid generating all possible substrings of the string naively. This approach is computationally intensive, with a time complexity of n cubed, and is rarely the most efficient way to solve the problem. Instead, strive for optimized parsing techniques. Another frequent issue is not using a set to enforce uniqueness. If duplicate numbers are counted multiple times, the solution will be incorrect. A set is a simple and efficient way to ensure that each number is only counted once. This not only reduces errors but also enhances the performance of your solution. Shifting focus to interviews, it's essential to recognize common patterns in problems like this. Techniques such as sliding windows, two-pointer approaches, and regular expressions are foundational tools for substring manipulation and digit extraction. Practicing these will significantly improve your problem-solving flexibility. Always remember to check edge cases, such as empty strings, strings with no numeric content, or very long strings with repeated patterns. These are scenarios interviewers often use to test your thoroughness. Additionally, be prepared to discuss the trade-offs between brute force and optimized approaches. For example, a linear pass to extract digits combined with a set for uniqueness achieves n complexity. Lastly, clear communication is key. Walk through your thought process, especially when dealing with tricky aspects like leading zeros, large numbers, or invalid input. This problem also shares concepts with several other related problems on LeetCode. For example, problem 3, longest substring without repeating characters, involves substring manipulation and ensuring uniqueness, which is highly relevant. Problem 159, longest substring with at most 2 distinct characters, is another sliding window problem that focuses on substring properties. Similarly, problem 187, repeated DNA sequences, requires extracting unique substrings from a string, while problem 266, palindrome permutation, deals with character frequency analysis, a related string processing concept. Beyond this, there are alternative approaches you can explore. One option is using regular expressions to extract sequences of digits directly. This method is concise and elegant, but it requires familiarity with regex syntax. Another approach is the sliding window technique, where you use 2 pointers to dynamically adjust the window over digit substrings. This is often more efficient but requires careful management of the pointers to ensure correctness. A third alternative approach is iterative parsing. In this method, you traverse the string character by character, building numbers incrementally as you go. When a non-digit character is encountered, you reset the current number and continue. This approach is memory efficient and straightforward to implement, but it can be error-prone if edge cases aren't handled properly. For example, it's easy to miss scenarios like strings with only non-digit characters or numbers separated by multiple delimiters. Regardless of the approach you choose, the key is to balance simplicity, efficiency, and robustness, ensuring your solution handles all edge cases and operates within optimal time complexity. Great job following along. To wrap up, we reviewed the solution, discussed key takeaways, and highlighted the importance of efficient string manipulation and set operations. If you found this helpful, please like and subscribe to stay updated with more problem-solving strategies. Keep practicing and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!